Okay, so here we go. We're going to start this problem, and as you can see, been able to write the shear force and bending moment as functions. We're going to have to deal with two regions. One region from 0 to 12, and then from 12 to 20. I am going to start by finding my reactions at A and have those available to me for checking down the road. So the first thing I'm going to do is I'm going to use this as a free body, and I'm going to come over here and establish positive shear and positive bending moment at A. And to make my calculations a little easier, I'm going to get a concentrated equivalent of that distributed load. It's a rectangle, so it's just going to be base times height, which is 48 kips. And the distance from A would be 6 feet. Okay? So I'm just now going to use my equations of equilibrium to find these reactions. So I'll start first by summing moments at A, making sure we have equilibrium. Again, I'm using right-hand rule for my sign convention. So starting on the left side, what kind of moment is that? Positive or negative? Negative. About A, both these forces create what kind of moment? Positive or negative? Negative. So that'd be 48 kips times 6 feet and 20 kips times 20 feet. So it looks like the moment is going to be negative, and whatever that is. I don't know what that is. 688. I guess I did know it. Sorry.
Rain Man there.
Okay, then we'll sum forces in the y direction. Make sure they're in equilibrium. So this force is acting up, down, down. So 48 kips down, 20 kips down. So what's my shear force? 68. So it looks like I have a positive shear force and a negative bending moment at A.
So if you had, for instance, this is a different beam, you had an X component for a reaction at B, would you still just ignore the axial force at A? Since we just focus on shear and moment, or would that affect shear and moment?
It will not. But we might have an axial force. And in general, you can have an axial force, and you would have an axial force diagram. It's just typical in beams that there is very little axial force. Now, when we switch to frame shear force and bending moment, then axial force comes into play quite a bit. And what's axial in one element could be shear in another element as it rotates through the structure. So, save your curiosity, Mr. Story, for about a week. Okay, so what we're going to do now is we're going to cut this structure somewhere from 0 to 12. Now, do you guys want to work the left side or the right side? Maybe I'll just kind of imagine it cut here at some distance x. Left side, right side. I think the left side is going to be a little easier to deal with. So I'm going to label this as a cut somewhere between x between 0 and 12. So this set of equations I'm going to develop are only going to be good when x is between 0 and 12. It can't be greater than 12. If it goes greater than 12, then my load changes and I go into a different area.
So you cut that wherever you want to.
I'm cutting it anywhere I want x, but it only is between 0 and 12.
Are you choosing to do that at the left side of the 48 kips or a...
No. That 48 kips is not there in that cut. Because when I cut it here, I'm going to be looking at this part of the loading diagram.
Okay.
So let me draw the free body diagram. I think you'll see it.
So that's why you cut it to the left of the 48.
I could have cut it to the right, but this is going to be a little more complicated to describe as a function of x. This is going to be very simple to describe as a function of x. Right? Because the distance is just x. And what do I have is I have positive shear of 68 kips, and I have a negative bending moment of 688 kip feet. That's the stuff I just found here. I just put it over there.
I have one more question.
Sure.
If you don't want the 48 kips in there, could you set your equation as...
Okay, wait. The 48 kip is only there as a concentrated force equivalent of the whole force.
Right. So
Okay, I'm not looking at the whole force now. I'm looking at some piece x of it. So there is no 48. I just want this part of it. So what would that be? So let's look at this diagram. So I'm still saying this is 4 kips per foot for the height, but now I'm cutting it at some distance x. So what's the concentrated equivalent for this section? Base times height, which will be 4x. Now when x is equal to 12, what do you get? 48. This is good now for any distance x between 0 and 12.
So why would you do 0x and 6 if you're to the left of the
But I don't want it at 3 points. I want it at every point x. I don't want it at 0 and 6 and 12. I want it everywhere. I want it every point you can imagine between 0 and 12. Infinite number of points. So what's the distance from the centroid to the cut surface? Half the distance. The distance is x. X over 2. Then I come to the cut surface and I apply positive shear, positive bending moment. So there's my free body diagram. All I do now is just what? Do equilibrium. So I'll start with summing moments at the cut. And what do I have? I'm using right-hand rule for my signs. So this moment becomes positive. The moment about the cut due to the 4x load is also positive. So the force is 4x. The moment arm is x over 2. So just so you don't forget, I'll write here that this is the force and this is the distance. Force times distance, right? Then I got 68 is creating negative moment. And what's its moment arm? X. And then I have this moment here at the end. That's positive. So I just solve for the moment. It will be a function of x. So what do I get here? I get 2x squared. I'll put a bracket here so I can put my units on the end. So I'll get minus 2x squared plus 68x minus 688. And all those terms should give me kip feet. Now, just like in our previous problems, can I check that to make sure I'm right? Well, the only thing I know about the left side of this is what? I know the moment. So I know the moment when x equals 0 should be minus 688. And I think you can see if you plug in x equals 0, you get minus 688. That's all you can do. You can't use this expression to come over here and check the moment at B. Why? Well, B is at x equal 20, and this is only good from 0 to 12. So we're stuck. We're not stuck. We stop. The next thing we can do is sum forces in the y direction. So we'll do that. Shear is acting down. Our equivalent force is acting down. The reaction force is acting up. So when I solve for shear as a function of x, I get minus 4x plus 68. And that should have units of kips. Do I know something about the shear on the left-hand side? I know when the shear, what is the shear at x equals 0? 68. And what does my equation tell me? At x equals 0, I get 68. Check. Now, is the derivative of the moment equal to the shear? The answer is yes. So that makes me feel pretty good. So I'll write here that the derivative of the moment with the shear, for that one, I'll also give it a check. So I'm feeling pretty good about that right now. But I'm only halfway home. I've only got shear force and bending moment equations for x equal 12. So what do I have to do now? Right, so let me slide over here and let's go from 12 to 20. So now I'm going to cut the structure somewhere here. So this was my first cut 1, this is my second cut 2. You want to work the left side or the right side? Oh, please say right side. Did everyone agree with me? I think the right side is the best side. So let's do that. I will draw a free body diagram of the right-hand side. There it is. 20 kips. Now the distance to that cut is still x. So what does the little piece of the free body have to be then? 20 minus x. Everybody see that? I have positive shear force, positive bending moment. And that's my free body diagram. That's a whole lot easier than thinking about all the stuff here on the left. So far, so good? So let's go ahead and do our statics then. So I'm going to sum moments about the cut and put an equilibrium. This moment with my sign convention is negative. The moment created about the cut with the 20 kip force is also negative. What's its moment arm? 20 minus x. So therefore, what is the moment as a function of x? Looks like it's 20 times 20 minus x. And that would have units of kip feet. Do you have to multiply it out? No. Does it work? What do I know about the moment out here on the free end? So that means that the moment at x equal 20 should be equal to 0. Is that true? Yes. You put in x equal 20, you get 0. Exciting, isn't it? So then we'll sum forces in the y direction. I've got a shear force acting up, 20 kip force acting down. So it looks like my shear is simply 20 kips. Pretty easy equation. I'll talk to you about what this means in a second, but let's check this. If you take the derivative of the moment with respect to x, is it equal to the shear? Take the derivative of this with respect to x. It's 20. Cool. Now I do want to take a little time and talk to you about what it means for the shear to be here on the end. So I'm going to sneak up and steal this little top corner section and draw a free body diagram of a little teeny tiny sliver of the end of that beam, where on the right hand side is my 20 kip force, and on the little sliver on the left is positive shear. Yeah.
Does it matter that the derivative is at negative 20?
Did I screw up? Oh, wait. This needs to be a minus here. Sorry. I lost my minus sign. Thank you. Now it's good. Thank you, Mr. Story. Yeah, there's a minus sign here. Make sure you check that. Okay, so when I go back up here and I sum forces in the y direction equals 0, what does it say? It says shear is equal to 20 kips. So that does check. But sometimes when you look at a point, you go, well, what is the actual shear under the point? Doesn't make any sense. But if you go just to the left, you can get it. Now what's the shear just to the right? It's 0. You're off the beam. Okay, so the last thing I could do, just to make myself feel really, really good about this, is I match these two. So I'm going to go back and call this section 1, and then call this one section 2. And I'm going to look that the moment from section 1 at x equal 12, is it equal to the moment in 2 at x equal 12? So somebody has to evaluate this at 12, and somebody has to evaluate this at 12. I can do that. That's 160. Does this come out to be 160? Should be negative 160, by the way. Can somebody put in 12 there and do that real quick? While they're doing that, the shear from the first section at x equal 12 should equal the shear from the second section at x equal 12. Now, I can do that. You put in 12 here, you get 20, and that's 20. So I know that one works. How about this one? Anybody finish that yet?
Minus 160.
Minus 160. Ta-da! So everything checks. Any questions? Okay, I'll turn that off.